Bueno, ¿qué tal? Buenas tardes, boa tarde, good afternoon para todos. Bueno, estamos empezando formalmente, si bien a la mañana ya fueron los cursos, estamos inaugurando el tercer encuentro argentino de cuerpos finitos. El primero fue en 2017, el segundo en 2019, y ahora los estamos haciendo al tercero virtualmente, lo cual, si bien por un lado a mí no me gusta estar así a través de pantallas y no vernos personalmente, tiene la cosa buena y linda de que podemos contar con mucha gente de afuera, brasileros, hay gente viéndonos de Canadá, de Estados Unidos, de Perú, de Chile, seguramente me olvido de algún otro
México.
país. Sí, México, no. Y bueno, este,
Colombia.
así que la verdad que es una oportunidad que tenemos ahora de expandir un poco esto. Hace poco hubo un congreso, un evento muy similar ahí organizado por Cicero y sus colegas bueno, no sé si en Uberlandia, en Brasil. Así que bueno, esto va en la misma sintonía. Así que bueno, voy a presentar al primer conferencista plenario, que es Cicero Carvalho. Estuve ahí hurgando un poquito en su página, en alguna página que encontré, y bueno, no fue sorpresa porque lo sabía, pero recordé que él se ha recibido de físico, además de matemático, ¿no? En la Universidad Federal de Río de Janeiro en los años 80 y 81 obtuvo esos títulos. Luego hizo una maestría en el IMPA en el 86 y el doctorado obviamente también en el IMPA en el año 94. Y luego hizo un postdoc en Harvard, ¿sí? En el 98. Y bueno, actualmente, como todos saben, está en la Universidad Federal de Uberlandia. Así que bueno, un gusto para mí que sea él, está también en el comité científico, que sea él quien inicie este congreso. Así que bueno, un gusto enorme presentar a Cicero Carvalho y lo dejo con él. Muchas gracias, Cicero. Adelante.
Bueno, Ricardo, muchas gracias por esta introducción. Bueno, yo pido disculpas, pero yo prefiero hablar en inglés porque por causa de los termos técnicos. Pero si hay preguntas, por favor, ustedes pueden hacer en español los que desean. Y yo puedo contestar en español también, o portuñol, digamos. I'd like to thank the organizing committee for the invitation to talk in this meeting. And I would like also to congratulate the organizing committee, because even though this is just the first day of the meeting, it's already very clear that this will be a very successful meeting for me. And I congratulate especially Ricardo, who has been talking to me about this meeting for at least 2 years. So, but all you guys from the organizing committee, thank you very much and congratulations. We have people from at least 10 countries. So you very well done job. Okay, so my talk will be about locally recoverable codes. And so I'll just start by defining some things that we all know, but just to establish notation. So FQ, as usual, will be a finite field with Q elements. We know that a code C of length M is just an FQ subspace of FQ to the M. We know that the vectors of the code are called code words. And given two M tuples, alpha and beta, in FQ to the M, we know that the Hamming distance between these two code words is just the number of positions where you have distinct entries in the code words. And the minimum distance of the code is just the minimum of the distance between two distinct code words. And because the code is a FQ subspace, this calculating the minimum of this distance amounts to calculate the minimum of the distance of a non-zero code word to 0, and the distance of a non-zero code word to 0 is just what we call the weight of the code word, which will be denoted by this omega. Okay? Okay, we all know this. So how to define codes? So this is the first question. Since codes are subspaces, you would think that it suffices to take a linearly independent set and think about the space generated by this set. But if you do that, it will be very difficult to determine the minimum distance. So there are several papers on this. I just listed one here that has this very, the name with a very impacting name. The intractability of computing the minimum distance of a code, even if you work over F2 and even if you use computers. So what we do is frequently we see codes built from starting from geometric or algebraic structures in a way that properties of these structures are used to determine the minimum distance, or at least a bound, usually a lower bound for the minimum distance. So for example, Goppa's theory of algebraic geometry codes uses this, starts from places in function fields. And in the beginning of the theory, you already have a lower bound for the minimum distance of the codes that he constructed. Okay, so the codes that we present in this talk will belong to the class called evaluation codes. So the idea is to start with a subset X of the affine space. So we have a certain number of points. Let's say that you have M points. Then you consider this I sub X, which is the ideal formed by all polynomials in the polynomial ring, which are 0 in every point of X. Okay? So you can consider the evaluation map, which that goes from this quotient ring to FQ to the M, where you just take a class of a polynomial and evaluates in the points P1 to Pm. So this is clearly well defined. Also, it's clear that this is an FQ linear transformation if you think of this quotient ring as an FQ vector space, and given a subspace of this quotient ring, the image, before let me say that you can prove, it's not difficult to prove that the phi is actually an isomorphism of FQ vector space. And given a subspace, the image of the subspace using phi is just evaluation code associated to the subspace. Of course, it has length m, and this code, because phi is an isomorphism of vector space, the dimension of this code is just a dimension of L. Okay, so for such codes, we may use tools from Grabner basis theory in order to determine a lower bound for the minimum distance. So I'll say a few things about Grabner basis. So let me start by denoting by this script M the set of monomials in the polynomial ring. Monomials are just product of powers of the variables. Okay, so we endow the set of monomials with a monomial order. So what is a monomial order? It's just a total order in the set such that 1 is the least monomial, and if you have an inequality of monomials and you multiply both sides by a monomial, the inequality still holds, doesn't change. So this is a monomial order. Okay, so now given f a polynomial, non-zero polynomial is just a finite sum of monomials, possibly multiplied by some coefficients. So you have only a finite number of monomials which appear in the polynomial. One of them must be the greatest monomial. So this is called the leading monomial of f. Okay. Okay. So now, given an ideal in the polynomial ring, we say that this a finite subset of polynomials in the ideal is a Grabner basis for this ideal with respect to some predefined monomial order if the leading monomial of any non-zero polynomial in I is a multiple of the leading monomial of one of these guys. So this set is a Grabner basis if the leading monomial of any non-zero polynomial in I is actually a multiple of the leading monomial of these guys. And one can prove that if you have a Grabner basis, this set is actually a basis for the ideal in the usual sense of generating set. Okay? Grabner basis appeared in the PhD thesis of Bruno Buchberger. It appeared as a paper in 1965. And he showed that it started with a generating set for the ideal. One may enlarge the set by using an algorithm that he presents in the thesis that after a finite number of steps arrives at a Grabner basis. Of course, maybe later you want to do some optimization process and so that you have less generators and still have a Grabner basis. We are not worried about that. So he proved that you start with the generating set, you can enlarge the set and obtain a Grabner basis, a basis with that property I told you before. So his thesis was actually to determine a basis for the quotient, this quotient ring considered as a vector space. And he showed that such a basis is given by the class of the monomials in the set. Monomials which are not the leading monomial of any polynomial in I. So this set is today known as the footprint of the ideal. Okay? Okay. So we have so let me just recall these two concepts. G1 to GS is a Gregory basis for I if the leading monomial of any non-zero polynomial I is actually a multiple of the leading monomial of one of these guys. And the footprint is the set of monomials which are not the leading monomial of any polynomial in I. So it's easy to see that a monomial is in the footprint if and only if it is not a multiple of the leading monomial of any of these guys, if this set is a Gregory basis. Okay? So this provides a way for us to see the footprint in a way. If we associate it to this monomial, this n-tuple of non-negative integers. So for example, let's assume that an ideal in the polynomial ring in just two variables is generated by these three polynomials, okay? And that this is a Gregory basis for the ideal with these leading monomials, okay? So this is the leading monomial of the first one, leading monomial of the second one, leading monomial of the third one. So now we plot the points associated to these monomials, like I said here. So to this monomial, I plot the point 1, 7. To this monomial corresponds the point 6, 4. And to this monomial, we have the point 8, 1. Okay? Okay, if anybody has any question, please feel free to interrupt me. Now I will plot the points which are multiples of the leading monomial of G1. So all the points in this region corresponds to monomials which are multiples of this leading monomial. For example, this point here, this point is the point 2, 7, which of course is this monomial multiplied by x1. And we do the same thing for this monomial. So here we plot the points which corresponds to the monomials which are multiples of this monomial. And now we plot the points, all this region are points which correspond to monomials which are multiple of this monomial. So the points that are left here correspond to monomials which are not the multiple of the leading monomials of these guys. So these points corresponds to exactly to the monomials of the footprint. So this is a way to see the footprint, and maybe that's where the name comes from. Okay. Another two concepts that I want to introduce are the following. Let J be generated by this generating set, maybe not a Gregory basis, and we can define the delta set associated to the linear monomials of these polynomials as being the set of monomials which are not the leading monomials, or not multiple of the leading monomials which appear here. So it's easy to see that the footprint of J is contained in this delta set. Okay. Also, we will denote by Vj the set of points in the this should be a fine space, but anyway, k to the n, which are zeros of all polynomials in this ideal. Okay, and one may show that if the footprint of the ideal is finite, then we have this inequality. Okay, so now I present an example to which I will refer later. This example appeared in the thesis of Irán Lopes, and then later in a paper by Irán Lopes, Rafael Villarreal, and Carlos Renteria Marques. Okay, so we start with n non-empty sets of FQ. We denote by DI the cardinality of the sets. We assume here a technical assumption. Then we take X to be the Cartesian product of these subsets. So here we have a set of points in the affine space, and the number of these points is just the product of the cardinalities of these AIs, which I will call M. So in the polynomial ring, I define these polynomials f sub I, which is that f sub I is a polynomial in just a variable x sub I. And this x sub I minus all the elements of the set AI. So clearly the degree of this polynomial is the number of elements here, it's d sub I. And we let I be the ideal generated by f1 to fn. Okay, then X is, it's very easy to see that X is the variety associated to this ideal. And also it's not difficult to see that this ideal is already the set of all polynomials which are have the points in which annihilates in the all points of X. So this is what I was calling before A sub X. Now I just call I. So we will consider this subspace of classes, subspaces of that quotient ring, seen as a vector space. So I consider the classes of polynomials which are either 0 or have degree up to D. Then the image of this subspace using phi is a code, which is a subspace of FQ to the M, which we call a fine Cartesian code of order D. Okay, so one may show that F1 to Fn actually is a Greber basis for I with respect to any monomial order that you can think of. And the footprint has M monomials, the product of the DIs. This is easy to see, so to speak, because the leading monomial of F1 is just X1 to D1, the leading monomial of F2 is just X2 to D2, and then we take out all the monomials which are multiples of these guys. We are left with a rectangle or a cube or a hypercube, depending on the number of n. And so it's easy to see that the footprint has this number of monomials. Okay. As for the minimum, as for the dimension, so this is the length of the code. We already knew that. As for the dimension of the code, we have that the dimension of the code is the same dimension of this vector space because phi is an isomorphism. And one may show that if you take the classes of monomials which belong to the footprint and have degree up to D, so this is a basis for this subspace. So the dimension of the code is just a number of monomials here. And later I will show you how to count these numbers, okay? As for the minimum distance, we will do the following. We start with a class in L sub D, so the class of a polynomial, so the degree of the polynomial is at most D, and we would like to estimate the weight of the code word associated to this class, okay? So clearly the weight of the code word is just a number, total number of entries minus the number of entries which are 0. The number of entries which are 0 is the number of points that are zeros of F, points of X. And this is just a variety of this ideal, sum of I plus the ideal generated by F. Okay, so as I observed before, the footprint of this ideal is contained in this delta set of the leading monomials of the generators. Here we have the generators of I, the generate, and here the leading monomial of F. Now, I already told you that the classes of these monomials form a basis for L sub D. So we may assume that F, this F is actually a linear combination of these monomials. And we may assume that the leading monomial of F is an element of the footprint and has degree less or equal than D. Okay, so we actually can count the number of monomials here. So again, we just plot here the points that corresponds to these monomials. We take out all the monomials which are multiples of this first set, and then we take out the monomials which are multiples of the leading monomial of F. So the number of these monomials here is just the number of points in this region here. So we have the original footprint minus this area. So the number of monomials here is just the original footprint minus that area, okay? So this shows that this set is actually finite. So this footprint, I plus of this ideal, I plus the ideal generated by F is also finite. And then we have that inequality that I told you before, this inequality here. So now we will plug a series of inequality in what we had there. We had this equality. Now because of, okay, now because of this inequality, I have this inequality, and now I have this inclusion, which provides this inequality. And actually, we know this number, which is exactly this number here. And I recall that M is the product of these DIs, so we are left only with this product here. So actually, we see that the weight of every code word has this a number like this as a lower bound. And what we did is to calculate the minimum value for these lower bounds. The minimum value for these lower bounds is a number like this. which is a function of the di's. So here we have this K, we have this L, and this K and this L are determined in the following way. You write D as D1 minus 1 plus D2 minus 1 until you have a certain remainder, which is less than DK plus 1 minus 1. So that's how you determine K and L. And once you have K and L, you can calculate this number. So I showed that the minimum of these values is this number, and also that there is a class of a polynomial which has weight equal to this number, okay? So this, but I'm saying I did this, but of course, the first proof that this was the minimum distance was by Iran Lopes, Rafael Villarreal, and Carlos Renteria Marques, okay? Okay, so this is, so now let's move to locally recoverable codes. So in the so-called distributed storage systems, which are common when we store things in the cloud. Okay, so when we use this, we store the things in the cloud, what happens is that the data is split and stored in several servers. Okay, so when you want to recover that data, or you want to send the data that you stored in the cloud to some other place, when the tuple that will form it has data that comes from the blue server, data that comes from the green server, from the red server, and so on. Okay. Now, sometimes due to machine failure, one or more of these entries are not sent. So the code word is formed with an erasure, there's nothing there. So to address this problem, in 2012, Gopalan and collaborators, they introduced the concept of locally recoverable codes. So these are codes that they say that a code is locally recoverable with locality R if an entry at a position J of a code word may be recovered from the entries in at most R other positions of a set Sj. So for each entry, so for each position J, you have a set Sj of other positions, at most R other positions, and the knowledge of the entries in these R other positions determines the entry at that Jth position. Okay, in that same paper, the authors proved a version for the singleton bound, which holds for codes like they have defined, and the version of the singleton bound is this inequality. Okay? Okay. So later in that same year, Prakash and collaborators generalized the concept of locally recoverable codes to the concept of codes with R delta locality, also called R delta locally recoverable codes. So we take, sorry, we take R to be a positive integer, we take delta to be an integer greater or equal than 2. And a code is R delta locally recoverable if for every position J of the coder, there exists a subset Rj containing J, so they decide to include J in that set. It's just a matter of taste. Containing J and of cardinality at most R plus delta minus 1. Such that the entries at any R positions in Rj determine the entries at the remaining positions, which are at most delta minus 1. So the idea here is that if you have an erasure at position J, you may recover that original entry from the entries at most R positions in the set Rj, even if you happen to have delta minus 2 erasures in the recovering set Rj, because Rj, the cardinality of Rj is R plus 1 plus delta minus 2 at most. So you have the position J, you have R position that you use to recover the position J, and you still can afford at most delta minus 2 erasures. Okay, so this was a generalization. The authors prove a version of the singleton bound, which is good for the codes that this class of codes that they have defined, which is this one. And when a code has equality here instead of inequality, they say that the code is an optimal code. Okay? Okay. So now we will present a code which is a subcode of the affine Cartesian code, which is an R delta locally recoverable code. So this is a joint work with Bruno Andrade, Victor Neumann, and Antonio Veiga, professors from my university. Okay. So as before, we take this AI subset of FQ for I1 to N. We write D sub I for the cardinality of the AI. We take X to be the Cartesian product of the AIs, so that X has this number of points, which I call M. Again, in the polynomial ring, I define this polynomials F sub I for all I, and we take I to be the ideal generated by these polynomials. And then X is, of course, the variety of I, and I is the set of all polynomials which have X as common zeros. Again, I recall that I had, I take D greater or equal than 0 to be an integer. Recall that I had worked with this subspace, classes of polynomials which are 0 or have degree up to D, and the affine Cartesian code was the image of this subspace using phi. Now what we do is the following. We choose S to be a number from 1 to N. So we will fix this S, okay? Fix this S, and then we choose delta greater or equal than 2 to be an integer, such that ds, the number of points in A sub S, ds minus delta plus 1 is greater or equal than 1. Okay, so now we work with this vector space, subvector space of that quotient ring. So I take classes of polynomials which belong to L sub D, such that the degree of F, when considered as a polynomial in X sub S, is less than ds minus delta plus 1. Okay, and we defined our code C delta S, CD delta S, as being the image of this subspace using phi. Okay, so clearly it's a subcode of the affine Cartesian code. And we proved that this code is an R delta locally recoverable code, with R being this number, ds minus delta plus 1. I won't show the proof here, but it's this basically the same proof that will appear later in the talk. Okay, so to determine the dimension of this code, we proved the following result. We consider this set classes of monomials which belong to the footprint, have degree at most D, and the power of excess in this monomial is less than ds minus delta plus 1. Okay, so we prove that this is a basis for that subspace that we have considered. Hence, the dimension of our code is just a number of monomials here. Later, I will show you how to count these monomials. We also proved the following result. Let delta tilde be this sum. So the sum of di minus 1, I from 1 to n, except s. And then we add ds minus delta. Then the dimension of the code that we have defined is this number here for all d greater or equal than d tilde. So this is for those that are accustomed to work with the Reed-Muller code. This is a typical Reed-Muller situation. From d, when you have d from a certain point on, the dimension doesn't change anymore. Okay. Okay, so now let XS be the Cartesian product of all the AIs except AS. And we write CSD for the affine Cartesian code of order D, defined using the points of XS, not X anymore, XS. Okay, so let D be a number greater than 1, less than D tilde. Okay, if D is in this range, greater or equal than 1, less or equal than this number, then the dimension of the code that we have defined is the same of the dimension of the affine Cartesian code. But if D is greater or equal than this number and less than D tilde, then the dimension of the code that we have defined is the dimension of the affine Cartesian code less the sum of the dimensions of these affine Cartesian codes of these orders, but defined over XS. Okay? Okay. So as for the minimum distance of these codes, we also have some results. So let D be a number greater or equal than 1, less than this product. Write D in that usual way, so to speak, D1 minus 1 plus D2 minus 2 until we have a set remainder, which is less than DK plus 1 minus 1. So we have that. We proved that the dimension of the affine Cartesian code of order D is less or equal than this, the code that we defined using the same D, which is less or equal than this expression. This expression actually just came for free. This comes from that singleton bound. So I actually didn't prove this inequality. It's for free. Where there's an R here, R is just ds minus delta plus 1. Now, if you have this set of two conditions or this set of two conditions, then we have equality here. So the dimension of the minimum distance, the minimum distance of the codes that we have defined is equal to the minimum distance of the affine Cartesian code of order D. Okay, so again, another result, let D tilde again be this number. Okay, so we prove that when you plug in D tilde here, or D tilde minus 1, so we have equality in this last inequality here is actually an equality. So these codes are optimal, okay? And we have that the minimum distance of this code, when you plug here D tilde is delta, and we plug in D tilde minus 1 is delta plus 1, okay? And we also proved that in the special case where the subsets AI are fields, so they are not only subsets now, they are subfields of FQ. Then we have a converse for this last statement of this theorem. So if we have equality between these two minimum distances, then either this set of two conditions hold or this set of two conditions hold. Okay, so we have a sort of converse for the last statement of this theorem. Okay. Okay. So in 2016, Rowat and collaborators introduced the concept of locally recoverable codes with availability T. So this extends the original concept of locally recoverable codes. So these are codes where to each position J in a code word, there are associated T pairwise disjoint recovering sets, each with at most R positions, such that the entry at position J may be recovered from the entry at the positions in any of the sets. So you don't have now only one recovering set. You have T disjoint recovering sets, okay? So these are codes with availability T. So in a joint work with Victor Neumann, now it's a different work, in a joint work with Victor Neumann, we constructed a family of codes with combined features from the concepts above, of the concepts of this idea from Rowat, and also ideas from R delta locally recoverable codes. So what it did is the following. For certain positive integers, delta 1, delta t, and R1 to RT, we obtain codes such that for each position J, there exist T recovering sets, each containing J, such that these sets, when you take off J, you have pairwise disjoint sets, and also the cardinality of the sets is Ri is equal to Ri plus delta I minus 1, and the entries at any set of Ri positions in Rij determine the entries in the remaining delta 1 minus 1 positions. So we have codes with availability, so to speak, because we have several locally recovering codes, and we also can afford to have some erasures in these recovering sets, okay? Because of this last statement. And Ri positions determine the remaining delta I minus 1 positions, entries in the positions, okay? Yeah, maybe I'm saying, talking a little bit fast. If you have any doubts, please feel free to interrupt me, okay? Okay, so anyway, let me now present what we did. So again, we take the n subsets of FQ. Again, we take X to be the product of these AIs. We write D for the cardinality of the AIs. And so the number of points in X is the product of the DIs, which we call again M. Again, in the polynomial ring, we define this polynomials F sub I, and I is the ideal generated by F1 to Fn, and X is the variety associated to I. So as before, we have this evaluation morphism, okay, which just evaluates a class of polynomials here in the points P1 to Pm. And so now we do the following. Instead of fixing a number S from 1 to n, we will do the following. For all I from 1 to n, we choose delta I greater or equal than 2, such that di minus delta I plus 1 is greater or equal than 1. And we call this number R sub I. Okay? Now, again, let D be an integer greater or equal than 0. Then we define these classes. This is also a subspace of this quotient ring, seen as a vector space. We define this subspace. Classes of polynomials, which are either 0 or have degree at most D. And when we look at F as a polynomial in Xi, the degree is less than Ri. But now for all I, we don't fix an S anymore. We do this for all I, okay? And we call this CD bold delta. This will be the image of this subvector space, okay? So now let J be a number from 1 to n. So J marks a position here in this code word, okay? I don't know how to select this, okay. So we claim that there exist n recovering sets R1J to Rnj containing the position J. When you take out the position J, these sets are pairwise disjoint. And for each I from 1 to n, we have that the cardinality of these sets is equal to Ri plus delta I minus 1. And this is just D sub I. If you look, here's the definition of Ri. So you see that this number is just Di. And the entries of any set of Ri positions in Rij determines the entries at the remaining delta I minus 1 positions. Okay, so now I will give a proof of this fact, which is you can use the same ideas to prove the similar statement for the other code in the other paper that I told you about. Okay, so to prove the claim, we start with a polynomial such that the degree of the polynomial is at most D. The degree of the polynomial seen as a polynomial Xi is less than Ri, which again, I recall is this number, Di minus delta I plus 1 for all I, so that when we evaluate these points at this polynomial at P1 to Pm, we have actually a code word in the code that we have defined. Okay, so now let's let J be a number from 1 to m. So J marks here a certain position, which corresponds, of course, to Pj. Here, instead of working with positions, we may work with points because there's a bijection, an obvious bijection between the positions and the points. So I start with the position J, which of course corresponds to this point Pj. Okay, so f of Pj is the jth entry in this code word. Okay, okay. So now let R be a number from R1 to n. So what I do here for I do for all these numbers. So let Rij be the following set of points of X. So I fix the entries of Pj, all entries except the ith entry, And the ith entry, I let it vary in A sub I. Okay, so we have a subset here of points of X. Of course, Pj belongs to Rij. The number of elements in Rij is exactly the number of elements in Ai, which is Di, which is that number that I wanted. And it's easy to say that when I take out, or in other words, when I make the intersection of two distinct sets like this, I get only Pj. Okay, so this already proves lots of things in this claim. So proves that we have any sets, prove that when we take out J, they are pairwise disjoint, proves that the set has this cardinality. Now we are only left to prove that any set of Ri positions determine the entries in the remaining delta I minus 1 positions. So we prove this now. So for this, we write f as a polynomial in the variable xi. Okay, so when I write f in the variable xi as a polynomial in the variable xi, the powers here go from 0 to Ri minus 1 at most. We have some coefficients here, which are polynomials without the variable xi. Okay, so clearly, when you take one of these coefficients, gv, and you evaluate in these points, the result is always the same because gv doesn't have the variable xi. So you have always the same result for a fixed v. So let's say that gv evaluated at any point yields always this result, which we call CV. And suppose that we know the values E1 to R, which I call E1 to ERI of F evaluated at Ri distinct points in this set. So suppose that we know these values, okay, for Ri distinct points. So this means that we know the result of sums like this. Here we have that result, CV. We know the result of sums like this for Ri distinct values of B. Let's call these values B1 to BRI minus 1, or B1 to BRI. Okay, so we know this these values EJ here. And now we may rewrite these equations as this matrix product. So we know these BIs, we know the result, and we may solve this system because this is clearly a van der Waals matrix. We may solve the system and find these values here. And as soon as we do that, now we may evaluate F in all points of Rij, because we already know the value of this CV here. So we just plug in all the values of AI here. Okay, so this is how the knowledge of Ri points, the values of F at Ri points determine the value of the other Di minus 1 points. Okay. So how about the dimension of this code? So we have that X, I'm just recalling things here. We have that X is the variable. We are working with the evaluation of this subset, this subspace here. Okay, so what we did is that we proved that if you take the classes of monomials, which are in the footprint, have degree up to D, and the power of Xi in each monomial is less than Ri, if you have this, if you consider this set, you may prove that this set is actually a basis for that vector space that we have considered. So the dimension of our code is just the number of monomials, of classes here, or monomials, because for each monomial there's just one class. For each class there's just one monomial. Okay. So so now we get to that point. How to count this? So using that there is a bijection between the set of monomials in n variables of degree up to D and the set of monomials in n plus 1 variables of degree exactly D. So there's a clear bijection between these two sets, monomials in n variables of degree up to D and monomials in n plus 1 variables of degree exactly D. So one may show that the number of monomials here is actually the coefficients of T to the D. T here is just a dummy variable. So B is equal to the coefficients of T to the D in this power, in this product. Okay, so here I will, the coefficients here will correspond to monomials of in n variables when I multiply here, and if necessary, I complete the power of T to the D, then this is the accounts for the extra variable. Anyway, this is something that easy to see. We may replace, of course, this sum by these quotients. Okay. Okay, so we have that this D of T is this. Here is just a formal situation, but sometimes people are picky. So you may think of dt as a real function of one variable defined in this region if you want. If you don't want, it's okay too. But if you think like this, you will replace easily this series by this function, 1 over 1 minus t. So we now may collect all those denominators here. Okay, and now actually there is you can expand this function, this rational function, as a series. Okay, and then you can also do this product, like say by hand. So you replace this expression by this series. You do this by hand, so you get 1, then you get minus the sum of minus times this powers of t. When you take 2 powers, you have a plus sign here, and so on. Okay, now you just have to figure out what is the coefficient of T to the D in this product, and this is not really something that is really hard to figure out, and it's this number. So this is how we calculate the dimension of this code, and also the dimension of all those codes that I presented before, even the affine Cartesian codes. Okay, and also as for the minimum distance, we proved the following results. So let m of S1 to Sn be this function, so to speak, of this Si, okay, with Si in this range, greater or equal than 0, less or equal than Ri minus 1. okay? And let D be an integer such that is in this range. Then the minimum distance of this code, the code that we have defined, is equal to the minimum of this function, of these integers, where the SI vary in this range, but also the sum of the SI is less or equal than D. So how do we prove this? The same way that I showed you that I proved the minimum distance of the affine Cartesian code when I used this picture, okay? So we proved that every code word has a number like this as a lower bound, then of course, the minimum of these lower bounds is a minimum for the minimum distance. You just have to prove that this minimum is realized, and actually it is. But maybe you'll say, but Cicero, in the case of the affine Cartesian codes, you had a closed formula for this minimum, which is the formula that Iran, Rafael, and Carlos have found. So there was a closed formula for this minimum. So how about in this case? Well, in this case, we only managed to find a formula, a closed formula for this special case where delta 1 is less or equal than delta 2, and so on, less or equal than delta n. In this case, we actually found that the minimum of this function with those restrictions in the SI is this product here, this product, okay? Where, of course, K and L are defined in the usual way. And we actually have examples that show that this condition is necessary. So we have we have examples where we don't have this condition, and the minimum distance is actually less than this number in this formula. But of course, for when we have this special condition, then we can calculate the mean. Okay. So this is I wanted to tell you today. I thank you very much for patience of hearing me for almost 50 minutes maybe. So thank you very much. Muchas gracias. Muchas gracias a todos.